Good morning, everyone. Today we'll be starting the section on semantics analysis. The lexical analysis part is over, and also the syntax analysis. The main task of lexical analysis was, you can remember, the generation of tokens. In syntax analysis, the main task was using the parser, either using top down or bottom up, the parse tree to be formed. Now in the semantics analysis, the evaluation of the tree to be performed. Now what is the evaluation of the tree? If you can recall that the first three stages of compiler designs are dealt with, actually mostly dealt with finding the errors in codes that you have written. Syntax, semantics and lexical. Last three stages, code optimization, final code generation and intermediate code generation. They are mostly involved in generating machine level code and optimizing the codes at the same time. Now, in the semantics analysis, what sort of errors actually are being tracked down? Let us see that segment first, then we will be moving to the other parts also. Okay. Okay. Now we are going to start the semantics analysis part. Now here, let me choose a pane from here. Okay. Now, you know that when I have a code, then that code actually here the character stream here, this is character stream. So character stream is fed through here by the scanner, right? The scanner is sometimes known as a lexical analyzer. This is lexical analyzer. And through this lexical analyzer, once it's processed, it enters through the parser. And here the output is token from the first. You know that mostly here we use the regular grammar segment. That's why I also have mentioned the term. So scanner or the lexical analyzer dealt with the regular grammar, and it has a complexity of order of n. Because you know now that we design a finite state machine where the state transition diagram are being designed, correct? So to find from a state, if I have to navigate this state, so this number of nodes I have to visit. So that's why it has a linear time complexity order of n. Because our task was in the lexicon analyzer to find whether the code contains any sort of errors. Also at the same time to segment whether it is a token or valid token or not, right? In the parser phase, that we seen that two parser are there, top down parser and bottom up parser. And in that segment, we see that the tree was formed, correct? Mostly though, we have not seen the tree in our examples. Rather, we have seen that what is called top down, what is called bottom up, what is called LL, LR, SLR. But mostly you have to remember that once a parser to be applied, either from top to bottom or bottom to up, with respect to a certain grammar. I hope you can remember one example I shown in the very beginning of the parsing technique, that to find if a tree is being given to you, correct? If that in that tree, if someone asks you how many childs are there, then you have only one option is there, that you should start from here and you should start counting from here, not from leap to from bottom to up. It is not possible. From top to bottom you should approach, because you need to check this tree here, you have to approach. But at the same time, if there is a someone has asked you to compute the value of 2 minus 5, you cannot start from top to bottom manner. You need to approach from bottom of matter 2 minus 5, or even let there is a plus is there, here 3 is there. So definitely you need to approach from bottom up, right? So the syntax tree definitely is being formed. This is a syntax tree, this is a syntax tree. Sometimes you have to approach from top down manner. Sometimes you have to approach in bottom up manner. If you are approaching bottom up manner, then definitely you are using LR parsing technique. If you are following the top down manner, then definitely you are following LL parsing technique. right? Now, depending on the scenario, the associated grammar will be applicable, right? Now, if I see the diagram again here that I was showing, let me erase the rest of the segment so that you can focus on what I am telling here. Okay, so after the parser, here the output is tree, correct? And you know that mostly here we deal with the context free grammar. I said regular grammar was there in the scanner phase or the syntax analyzer, sorry, lexical analyzer phase. Context free grammar was there in the parser generation phase or the syntax analysis phase. Correct? And the output from this tree, whatever the tree we obtain, sometimes this tree is called abstract syntax tree. Why the abstract syntax tree? Because once a tree being formed, this is a tree being formed, this tree I evaluate from either top down or from bottom up, right? But how to calculate the internal node values, this node value, this node value? So what are the rules to be applied? That are called, the rules are known as semantic rules. Okay, before evaluation of the internal nodes, I cannot find the root node value, right? So I can form a tree, I can decide I have to approach in top down and bottom up using that LR or LL grammar. But in a way to calculate the internal node values, you need to take help of semantics analyzer. After that only you can reach out to the root node and subsequently you can find the value, right? So that's why the syntax tree that I have obtained in the syntax analyzer phase, that is called abstract syntax tree. Abstract because it is not a complete syntax tree that we are expecting, right? Once it is being done, then it passes through the semantics analyzer. That means the tree without the evaluation of internal node values are termed as abstract syntax tree. Once the internal node values are calculated and at the same time the root node value is calculated, as a whole we can tell the tree value, the entire tree value means -2, here it is plus, here it is 5, here it is 3. So internal node values we calculate and finally the entire tree value once we calculate, that is the main task of semantics analyzer. They need to give the exact expression of the entire tree. That tree is known as here complete syntax tree. Initially it is abstract syntax tree, here we are obtaining the complete syntax tree. Syntax tree. Okay. Once this phase is over, then you can check the grammar, whatever the outputs are generated, it will come here and it will passes through the intermediate code generator and then code optimizer and then final code generator or machine readable code. Okay. Already you know all the phases. In the very beginning of the compiler design paper, we discussed on that and different phases I explained there, right? Now we'll be looking at some more aspect here. The first thing is that in lexical analysis phase, what we seen that if some mistakes were there. For example, I said I had to that int a1 is a valid description, but if I write int 1a, so that is an error, correct? And this is a lexical error, correct? I am writing here a lexical error because 1a is not accepted by the finite state machine and subsequently errors are being thrown, correct? At the same time, we seen that if we write instead of if I write phi x equal to 2, then if I write something, then definitely it finds that phi is not a valid. This is x equal to 2. Here we are performing a matching, but phi is not a valid keyword. So this error belongs to the category of syntactical error. And also is seen what is called lexical error, right? So lexical error may have different categories. For example, here also I have given some of the lexical errors. Let me minimize the screen so that you can see it clearly. Okay. Lexical error means you see the first point, multiple declaration. Multiple declaration means here x equal to 2 you declared int x. Again you are declaring x equal to 2. Now you see that from your computer perspective, int x equal to 2, int x equal to 2, this is a valid syntax. There is no problem with that. Lexically it is correct. Syntactically also it is correct. Let if I again declare int x equal to 2. Both lexically correct and also syntactically correct. But semantically they are incorrect because twice how I can declare a variable. Right? So this is not specifically possible. So to take a sense that I have declared a variable twice, we need a grammar. That grammar is very sensitive to the language. The language is here, which is very sensitive to this language. That's why we are applying context sensitive language in semantics analysis phase. This sensitive language tracks that twice you have declared it. Lexical analyzer, regular grammar. Syntax analyzer, context free grammar. Semantics analyzer, context sensitive grammar. Now I hope that you have understood why the sensitivity is required. Let's take one more example over here. For example, time mismatch problem. Time mismatch, already I explained that part, that if let int x equal to 2, you have said, and you are writing character ch. Both are valid declaration. No lexical error, no syntactical errors are there. Now you are assigning ch equal to x. Syntactically correct, lexically correct. But you are assigning an integer variable to a character. So proper typecasting operation to be performed over here. So here the sensitivity remains because you are assigning a integer variable to a character variable. The proper syntax would have been ch, and you have to convert it into character first, this x, and then only to be assigned to ch. This would be the correct syntax. But if you try to execute this code through a compiler, then it will execute. But certainly at the end of the execution, means after the compilation, it will show a warning that incompatible operand, like that messages may show that you are assigning a character variable to an integer value to a character variable, but still your code may execute. But semantically you are wrong. So this error comes under the category of semantical error, right? Or even, for example, wrong, you see that number different cases I have written out here. Wrong argument, or even array out of bound. Yes, this is a very valid part, right? Let I have written integer a10, right? Or let integer rather a10, I'm writing a3. So integer a3 means I have declared three cells. I have a cell a0, I have a cell a1, and also I have a cell a2. So these three represent the size. So 3 indexing starts from 0 and it up to 2. But now let a0 equal to 55 you are storing, a1 equal to you are storing 66, a2 equal to you are storing 77. But now you forcefully you are assigning a3 equal to 88. What happens? So this is not a valid code you have written out here. Valid code in the sense that you had only 3 memory spaces, but you are using 4th memory space out here to assign a new variable or value, static value. So this is, you are operating beyond the size. So this is also a sensitive matter. You have a capacity of pending, you have a capacity of lending, let $100, but you are lending someone with $120. So it is beyond your capacity. So that means you need to sense that this is not in your capacity to give someone $120 if someone asks you as a lend from you. Right. Another point is that wrong argument. Yes, that is also a valid point. Wrong argument means, let me erase this portion over here. Wrong argument means, let in the function, what you normally do, the function calling part, let you have a function add. You have called a function and you are here applying integer a, integer b, and float c, for example, right? So, and you are storing the value into here. This is a under, let this is I am writing under main, and a value, b value, c value are coming, and here you are printing the value for x. I am writing in pseudocode, correct? And a value is 10, b is equal to 20, and c does not have any value. Under the main, you have called a function, add function. You will be adding a, b value, and it will be stored into c. C is a float type. It should be the typecasting to be performed, but still I have written for a certain reason. Okay. Now see, if while declaring the function, let it is returning integer int, let for example here I have written, instead of int a, if I have written int x, int y, and int z. The first problem I am making, that here should be float. Here I am writing integer. So there is a sensitivity issue is there. Number of arguments also matters. So here the type of arguments, I am making a problem with the type of argument. Let also I make a problem if I have not declared int z, only int x and int y I have written. This was my mistake. How the compiler finds? Compiler checks that 3 arguments are here, but here you are writing 2 arguments. So this is also an error. Whether you make an error in the making the type declaration different for different argument, that is a problem. Or even if you make lesser number or higher number of arguments in the called function or even the calling function, that also create a problem. So these are all sensitive matters. This cannot be tracked by either lexical analyzer or syntax analyzer, because syntactically it is correct, and syntactically this one also correct, because this is a return type, this is a function name, this is an integer, it is an integer x, x has a type integer, y has a type integer, they are separated by a comma. Here there is a bracket is there, parenthesis, that means the bracket is there, then parenthesis coming, closing to the parenthesis. It is an absolute function that I am declaring. So no errors are there in terms of syntax analysis point of view, but the errors are there in terms of semantical point of view. Okay. So I hope you have understood what I have said, that the errors can now be of different types, lexical error or syntactical or semantical error. I hope now you have understood the different errors that already I have explained here. Now, under the semantics analyzer, what was our main task? Again, I am repeating. Our main task is to here that if a tree being formed, let minus, here I am writing, this is plus, this is plus, this is asterisk, let this is 3, this is 7, this is 2, this is 9. Now, to evaluate the tree, I cannot complete the evaluation of the tree in the syntax analysis phase. I can take a decision that I will evaluate the tree from bottom up. Correct? So the associated parser, for the parser and his associated grammar will be fired. On fired means I wanted to mean it will execute. So that means LR grammar, any of the LR grammar that are defined over that tree will be executing to find the value. But to calculate the internal node value, so 2 asterisk 9, it is 18. 3 plus 7, this value is 10. 10 plus 18, it is 28. So 5 minus 28 minus 23. So this value minus 23 to be calculated in semantic analysis phase. So the tree that is formed initially, that is called abstract syntax tree, that is being generated from syntax analysis phase. But after evolution of the tree, this is called complete syntax tree, and it is being done in the semantics analysis phase. Now we have to know that how this evolution, the 2 asterisk 9 means 18. Who says that this asterisk means multiplication of 2 with 9? It is also possible that asterisk means addition or asterisk means division. So we need to know the compiler that asterisk means you have to perform this with this. For example, asterisk means whether 2 multiplied with 9 or 9 multiplied with 2. You thinks that both are same. Yes, both are same. But in terms of division, if I write 2 divided by 9 or 9 divided by 2, because asterisk plus both are reversible operators. Either I can approach left to right or right to left. But minus and divisions are not reversible operators. They are unidirectional operators. So we need to associate certain rules while evaluating the internal nodes. This is an internal node. We need to have a rule over here that the first value to be divided with the first value to be divided with the last value over here, and the operation is here. That is called semantical rule. So that means for evaluating of each node, a semantical rule is required. I hope this is clear before you. The main task of semantical analyzer or semantics phase is to find a rule associated with each internal nodes and to find the exact value to be obtained from the leaf nodes, right? Okay. Now, if I I'm minimizing this window now, right now. Okay. Now, under the this phase, two actually categories are there under the semantics analysis segment. One is called syntax directed definition segment. Another is called translation segment. Again, I am telling that if you cannot remember those terms right now, then it is also fine. Once this semantics analysis phase, it is quite simple. Once it is being over, you can remember both the terms. Okay. So mainly two categories are there: syntax directed translation definition and translation key. Under the syntax directed definition, two subcategories are here. One subcategory is S attributed, another subcategory is L attributed. So the semantics analyzer, which operates over a grammar that is called attribute grammar. It is good to remember that mostly we say this is a context free grammar, context sensitive grammar, but it is good to remember that in semantics analysis phase, the context sensitive rules that I will be applying or we will be applying are over attribute grammar. Correct? It has two segments. One segment is syntax directed definition, another segment is translation scheme. Under the syntax directed definition, two subcategories are there: S attributed definition and another is L attributed definition. Right? Now we will be coming both the definition one by one, and we will be looking through all the segments one by one. Now first we will be focusing on the syntax directed definition. Correct? The first one we will be focusing on this part. Okay, I am marking it as a has. So this part we will be looking at. So syntax directed definition. Correct? Which I will be operating over an attributed grammar. Attribute grammar. That's why I have marked it here. Now, what are the rules in the syntax directed definition? That it is associated with set of attributes. You will understand these terms shortly. Productions are associated with semantical rules. That means here, whatever the production I will write, X to Y, Z. So once I write a production, it will have a rule. Why? because x to yz means x is generating here y here z. So how to evaluate this x to yz? What does it means? What does the x means? Y multiplied z, or y division z, or z minus y minus z, correct? Or plus z. So rules should be there with each production that I will be having. Because from this production only the syntax tree being formed, the abstract syntax tree being formed. So it is better to write the rules when I am defining the production rules. Rules mean semantical rules. Embedding semantical rules while defining the production rules are good before designing the syntax tree. Correct? Okay. Now, how the semantical rules are there? I hope here you will be getting the test that how the rules are there. Let me discuss some of the segment first. Then I will be coming to the categories later. I was discussing syntax directed definition, right? Our point is syntax directed definition. Definition, right? Now, under the syntax directed definition, what I said, two categories are there: S attributed, another is L attributed. Okay. Now here we will be mostly focusing on the S attributed definition. This S attributed definition has two segments. That means two phenomena. One is called synthesized, SIZDD, and called inherited. These are attributes. So S attributed definition operates over synthesized attributes and inherited attributes. Two attributes are there. We will be discussing on L attributed later. This is not our main focus, so just I am crossing out here. So our main focus is on synthesized attribute and inherited attribute, which comes under the S attributed definition, which is a category under the syntax directed definition. Right? Okay. I hope you can remember that semanticus and semantical analysis. Here, if I write the semantic analysis for your understanding perspective, here I am writing semantical analysis. Semantical analysis is segmented into two parts. Here, just already I have shown syntax directed definition and translation. So again writing syntax directed, another is translation. Okay, so translation does not have any different categories. Syntax directed had two categories. One is called S attributed, another is called attributed, another is called L attributed. Under the S attributed, we will be looking through two different attributes. One is called synthesized, another is called inherited. This is the architecture. I hope this will be okay for you. Semantical analysis, syntax directed definition, another is translation. Syntax directed definition has two categories: S attributed definition and L attributed definition. And S attributed definition can be performed either using a synthesized attribute or using by inherited attribute. Right? So today we will be focusing on synthesized and inherited attribute. Just I have taken some new pages where I can write some more examples to make you understand. Okay. Now see that what I was telling under the semantical rules, that two things I have said, that it operates over set of attributes, attribute grammar, and also it has some production rule. Just it has some production rules associated with some semantical rules. So set of attributes means either it will be synthesized or it will be inherited. And semantical rules means these are called semantical rules. These are called semantical rules. Now, if I write, let for a grammar G, this is a grammar G, and this grammar has this many production. Let this is a production number 1, 2, 3, 4, 5, 6, and 7 productions are there. For each production, certain rules are being associated. If L extends to En, it does mean I am printing the value for E dot val, the E value I am printing. If it there E2 E1 plus T, it means I am adding E1 dot val with T dot val. Right? Some rules are being defined. What does this rule means? Let's see, take one example that will be good for you. Let me draw this diagram first. L2 En. Okay, with the first production, that if I am drawing, let someone ask me, that will be good if I follow this structure. If let someone ask me to find it out, the structure for 3 plus 5 asterisk 4n, this is a string. This is for this string, I have to find it out a syntax tree. You know, na? You can remember in my class I said that here the plus, here 2, here if it is 3, then for infix operation, if you drop the node perpendicularly, then it will become as 2 plus 3. For in order, I said here in this way you have to traverse. For post order, you have to start from here and you have to reach out here. Correct? So this is the evolution of the tree. Now, here what they have said, that you need to design this string from these production rules that are given over G. Okay. Now how I am doing here? Now first I am starting with the first production, that is L2 En. Okay. Let me change the pen color bit, little bit. L is generating two values, either it will be E or small n, right? This is a parent production. And for L2 En, what we have to do, the associated rule is printing the E dot val. But here I cannot print right now because I have not formed the tree yet. Once the tree is being formed, then only I can evaluate the value. Okay. Then what I am doing, E is being expanded to E plus T. Okay. I am executing the second rule. Here I am applying the rule number 2. E is extended to E plus T. E1 means E actually. E plus T. Either you can write E1 or E, means as we are creating a new E node, that's why I have said E1, but E1 and E both are same. And E1 to E plus T, the plus operator is here. E1 plus T, right? After that, I am expanding E to T. Okay. I am expanding E to T. Why? Because we are applying the rule number 3 over here. It is not required that every time you will be following 1, 2, 3, 4, 5, 6 in this way, but for the necessity of generating this string, I am applying the rules. E1 to T. Then here again the T is being expanded. T to T star F. Then I hope that it will be better if you see this structure here. Let me zoom out. Okay. Here this is a root node. It is being expanded to here. This is E. Here this is N. E again expanded to E1 plus T using the rule number 2. E is expanded to T. Then again here T to T star F. T star, here it is F. Then F extend to here. Here it is 5. and f extend to 3, and because I have to generate the string 3 plus 5 plus 4, that's why 3 asterisk 5 plus 4. So here the 3 comes, here also the asterisk comes, here the 5 comes, here the plus symbol appears over here. Infix operation I am performing, t generate depth and f generate 4. So here the value is 4, and finally from here the n value is dropping and it is n. Correct? So our desired value is 3 plus 3 asterisk 5 plus 4n. That was our desired value. 3 asterisk 5 plus 4n. Right? Now, why I have designed this diagram again? Because this design diagram is using this production rule. Let's see, this production rule we have used, but no semantical rules yet we have fired. Right? So that means the design of the tree, I have designed the tree, correct? Up to that it comes under the syntax analysis phase. Now, if someone asks us to evaluate the tree, so that means definitely I have to approach from bottom up panel. So this also comes under the syntax analysis phase because we have to apply LR parser to traverse the tree from bottom up panel. Till now, we are in syntax analysis phase. But once we are start evaluating the internal node values, these are the internal nodes. These are the internal nodes. This one also. We have to apply certain rules. Those rules are called semantical rules, and those rules are being defined over here. Now, correct? Now see what are the rules they are written. Okay. Now I have to just scroll up, and again I have to show you that okay, better if I draw the diagram side by side. Okay, let me minimize the diagram because the diagram is quite large here. E to n, E is generating here E, here plus, here it is T, then here it is T is coming, then from T it is coming T, here it is star, here it is F, from T it is coming F, from F it is strictly coming 5, from F it is coming as 3, from T it is coming as F, from F it is coming 4, and 4 and nothing is there. Okay, this is the architecture of the tree. Take the eraser so that I can erase it. Okay. Now see, this tree is being formed under the syntax analysis phase. Now the semantical rules that are being embedded over here, that we have to apply them. We have to apply them. That means these are the semantical rules we have to fire. Still so far we have used only the production rule. And this production rule comes under a grammar. So the grammar we have used and the associated production rule we have used to generate a tree corresponding to the string 3 asterisk 5 plus 4n. Right? Now see that from rule number 7, if f2 digit is there, then f dot val means digit dot lexical val. So whatever the digit value is there, it will be assigned to f val. So that means for f2 digit production, f2 digit production. So f2 digit production is here. Let me change the pen color. F2 digit production is here. F2 3. Here also F2 5. Here also F2 4. So that means this F is containing the value itself 3. F is containing the value itself 5, F is containing the value for 4. So that means this internal node value as 5, this is 5, X, this is 4, 3, 5 and 4. Now for T2F, for production number 5, if T2F is there, that means T dot val equal to F dot val. You were assuming that T producing X, F, that's why directly it is written T dot val equal to F dot val, but always it is not possible. Sometimes you will see that it is being written F dot val again. T dot val means F dot val multiplied by F dot val. Then it aspect will definitely will change. T dot val equal to F dot val into F dot val, if I assume, then definitely T dot val, it will be the T value will be 3 you are assuming, but it value will be 9 now. Multiplied T F dot val twice, 3 into 3. Here also T2F, once the production is there, here the value is 9. Let me mark it. If I am taking that F dot val asterisk F dot val is a valid syntax. If F dot val, this portion is not there, then definitely instead of 9, it will be coming as 3. But let us proceed with F dot val to F dot val, because the simple example already I have evaluated in the class note, you can check out there. Let us go ahead with some complex scenario. F dot val multiplied by F dot val. So once T dot F, where is T dot F? Another area is there where T dot F is there, T dot F. So this value will be 16, correct? But here from T, F is not there because T is generating T star F. T dot F production is not used here. So I cannot use for this evaluation of the tree T 25. This is not possible, right? So T is 9, F is 5, capital T is 16, right? Let me change the color for the pen so you have to understand. Now T star F, let here they have written T to T star F. Let T star F in the rule number 4 means T1 dot val, F1 dot val. Let I am changing this T star F means they will add, for example. It is possible because T star or it may have a symbol has different symbol it may contain. That symbol may have a different semantical rule embedded in the compiler. You are expecting that star is there means it is asterisk, but instead of star it may contain has. Then what you will take? What is the meaning of has? Internally it may have written the has means plus. That is possible. Let I am taking it has. That will be good. T equal to T has F. Okay, let me change it in that way. Let it is has. So I have written it has. This is has. So T equal to T has F means in rule number 4 means T dot val plus F dot val. So T dot val is it is 9, F dot val is 5. So 9 plus 5 equal to, okay, it is 14, not 30, 14. Correct. Right. Now here again E to T is there. We are approaching in bottom up manner. Just see. E to T is there. So for what is the value for E? So here rule number 3. E to T means E dot val into T dot val. E dot val equal to T dot val. So 14 is being assigned directly to here. Let 14 is being assigned here. Now 14, E has 14, T has 16. So E to E plus T. Okay, this production number 2, E to E plus T means E dot val plus T dot val. So 14 plus 16 I have to add. So this E will contain 30. Right? And finally, L equal to En means print E val. So 30n is there. That means the value will be 30. They have written. There is no meaning of n. They are assuming n equal to 1. So the tree value is 30. Right? Now, how I have obtained the value for this tree as 30? by firing the semantical rules. Without the semantical rules, I only can design the tree. I can take a decision, I have to evaluate from bottom up. But once the semantical rules applied, that means once we are in the semantical analysis phase, the semantical rules to be embedded and subsequently we have to take a decision. Okay. So I am wrapping up today's class here. Tomorrow we will be covering the rest of the portions. Today we have just learned what are the different types in the uh, semantical analysis phase, what are the errors are being tracked, and just we started the S attributed definition segment, and yet we have not discussed on synthesized attribute and inherited attribute. But we have seen what is called semantical rule and why they are required. In why they are required means I wanted to mean that while writing the production rules in the grammar segment, why the semantical rules to be embedded? Because our motive is to change from abstract syntax tree to complete syntax tree, and final the evolution of the tree. So that part we have learned. Just you can remember only this thing tomorrow, and it will take some 3 classes, 2 to 3 classes to complete this thing. Today is the class I have taken. 2 more classes will require, and we will wrap up the semantical analysis.